Hello, George Romanic here. In today's video, we are going to introduce a new concept of omega vertical motion. What is this and why is this important? This concept is related to pressure coordinate system or isobaric coordinate system in which we use pressure to measure vertical distance from Earth's surface instead of geometric height as we usually do in everyday life. However, I have several videos demonstrating that pressure coordinate system has certain benefits in atmospheric sciences, and the most obvious benefit is that when we use isobaric coordinate system, density of air disappears in the expressions for horizontal components of pressure gradient force. And we don't like to use density in atmospheric sciences because it's difficult to measure. There are certain other benefits that we will see in future videos, but this is one of the most obvious and most important benefits of the pressure coordinate system. However, if you use pressure coordinate system, the question is, how do you define vertical velocity? Because in everyday Cartesian coordinate system, vertical velocity W is defined as dz over dt, some vertical increment over period of time, logically. That's vertical velocity. But there is no anymore vertical increment in terms of geometric height. Now we have pressure as vertical coordinate. So how do we deal with the concept of vertical motions if we introduce pressure as vertical coordinate? And that's where the concept of omega vertical motion gets in. So now, when you know the goal of this video, let's introduce omega vertical motion. Let's look at some generic function f that is function of x, y, p, pressure, and time t. Namely, instead of geometric height z, we use pressure as the vertical coordinate. And this function f can be really anything. It can be temperature, u component of wind, v component of wind, so on. Total derivative of this function f is df is equal delta f delta t dt plus delta f delta x dx plus delta f delta y dy plus delta f delta p dp. In mathematics, we say that total differentiation of a function is the sum that contains rate of change of that function with respect to all independent variables, and then we multiply these rate of changes with total differential of independent variables. For example, let's say that f is T, temperature, identically equal to temperature. Then we could look at the first term as delta T, where T is time now, times dt. Well, delta T over small delta T is rate of change of temperature with time, and then this is increment in time. So let's say that temperature is changing delta T over delta T in time for, I don't know, 1 degree Celsius in 1 hour. And now let's say that in total 1 hour or 5 hours, let's say, pass. That means that delta T times dt is equal 1 degree Celsius per 1 hour times the total time that elapsed, which is 5 hours, and that's the change in independent variable. Well, hour and hour cancels, and we get that this is equal 5 degrees Celsius. And that's the total change of temperature. We accounted for the rate of change across the independent variable times the change of independent variable. Okay, now let's go to this general equation over here, and we divide this equation by dt. We will get that df dt is equal delta F delta T plus delta F delta X dx dt is u component of wind plus delta F delta Y dy dt will be v component of wind plus delta F delta P dp dt will be now something that we call omega. And omega by definition is equal dp dt. And this is called omega vertical motion. We see that omega plays the same role in the pressure coordinate system that W plays in the height Cartesian coordinate system, and you will remember that W was equal dz dt. Well, now when we wrote these two equations, let's try to find relationship between omega and W. From this equation, we can write that omega is dp dt, that's just this equation, but dp dt we can write using substantial derivative as delta p delta t plus u horizontal dot nabla horizontal p and plus w delta p delta z, where h stands for horizontal velocity and horizontal del operator. And basically this is the relationship between the two. Now I would assume that some of you hoped for a much nicer relationship that looks like a neat equation, not this long equation, but that's how it is. We can make this look nicer if we adopt certain assumptions. And the only assumption that we actually need to adopt is that motion is in mid-latitudes and at large scales, what we call synoptic scales. Then we can use scaling arguments to demonstrate that the first two terms on the right-hand side are much smaller than this third term on the right-hand side. So let's do that. So let me first estimate the order of magnitude of this horizontal advection of pressure, namely this UH dot nabla horizontal P scales. And now you have to go and watch my video on the concepts of scaling, as well as video on scaling of horizontal momentum equation to understand what I will say. This term scales as characteristic value of horizontal velocity in mid-latitudes, and that's 10 meters per second, times the characteristic pressure perturbation, which we call delta P, over the horizontal scale L. And that is equal, well, 10 meters per second. Characteristic scale of pressure perturbations is 10 to power 3 pascals, and characteristic horizontal scale is 10 to power 6 meters, 1000 kilometers. And then if you calculate this, you get that this is 10 to power negative 2 pascals per second. Now if we scale the first term on the right hand side, namely delta P over delta T, that will scale as this pressure perturbation in synoptic scales in mid-latitudes, delta P over some characteristic Lagrangian time, tau. All these are explained in my video on scaling of horizontal momentum equation. And this is equal, well, the same 10 to power 3 pascals over tau, but tau I will rewrite as characteristic length over characteristic velocity, and then this becomes 10 to power 3 pascals over 10 to power 6 meters over 10 meters per second. And this is just equal 10 to power negative 2 pascals per second. So these two terms, as you can see, have the same order of magnitude. However, let's look at this term over here. This term, W delta P delta Z, scales as, well, characteristic value of W times pressure fluctuation but along the height, that is characteristic height, and that's basically depth of the troposphere. Again, all these are now explained in my video on the scaling of vertical momentum equation. So this is equal, characteristic value of W is 10 centimeters, is 1 centimeter per second, so 0.01 meters per second. Delta P is 10 to power 5 pascals, and h is 10 kilometers, which is 10,000 meters. And if you calculate this, you will get that this number is 10 to power negative 1 pascals per second. So you see that this term is one order of magnitude larger than the other terms. So if we accept this argument that follows from scaling, then clearly we can see that omega is approximately equal W delta P delta Z, and that is equal minus W rho G, where I use the fact that delta P delta Z is minus rho G, and that is hydrostatic approximation that holds excellently in mid-latitudes. I have videos on that if you want to check that out. So, for example, in this case, if W is 1 centimeter per second, which I used in this scaling, then that follows that omega is approximately minus 0.1 pascals per second. Yes, negative, because positive W means upward motion, and that means pressure is decreasing with height. So maybe it would be also good to write that down, so let's do that. Ascending motion means W is positive, but at the same time omega is negative because pressure is decreasing with height. Descending motion means W is negative, but omega is positive because pressure is increasing as we approach Earth's surface. I believe this concept was very simple. We introduce omega as a substitute for W in case of isobaric coordinate system, and we saw also what is the relationship between omega and W, where W is vertical velocity in Cartesian coordinate system. We will use these concepts in future videos to further explore atmospheric dynamics. Until then, goodbye.